First of all, welcome everyone to the Asia Pacific Analysis and PDA seminar once more. So today I'm very pleased to introduce Cristiana de Filippis. She's, I think, as of maybe this month at the University of Parma. She graduated with a PhD from Oxford quite recently, just last year, 2020, right? But as you'll see, she already has a rather remarkable range of results. She's going to speak today about perturbations beyond Schauder. Thanks, Christiana.
Many thanks, and thanks a lot for the invitation. In this talk, I will present some results concerning Schauder estimates for minimizers of non-uniformly elliptic variational integrals or for solutions to non-uniformly elliptic equations. Okay, let me start from the very basics and let's have a look to a linear equation, okay, which is minus divergence of x du equals 0, okay, and assume that A is symmetric. Now, what is uniform ellipticity? Well, I can define uniform, I can say that this equation is uniformly elliptic if the supremum of the ratio of the highest eigenvalue of A over the lowest eigenvalue of A is uniformly bounded, okay? Otherwise, this is said to be non-uniformly elliptic. Now, let me try to bring this concept of uniform ellipticity or non-uniform ellipticity into the nonlinear setting, okay? If I consider a nonlinear equation, minus divergence of A of du equals 0, okay? Now, if I want to get information about the regularity of the gradient, I need at least on a formal level to differentiate the equation. So if I look at the linearized equation, which is the one obtained by literally differentiating it, I have an equation of the type minus divergence of A of x d of dsu equals 0, okay, which is in some sense quite similar to the linear one that I showed you before, but this time A of x is the derivative in the gradient variable of the nonlinear tensor evaluated at du. But I repeat, this is quite similar to the previous one. Therefore, I can try to, in some sense, measure its ellipticity by considering the lowest eigenvalue of the z of A and the highest eigenvalue of the very same metric, okay? And then looking at their ratio. In general, when dealing with this kind of equations, I consider elliptic equations. Therefore, this quantity is non-negative. And what I get is that I'm dealing with a uniformly elliptic equation when this ratio is uniformly bounded. Otherwise, again, I am in a non-uniform ellipticity. I am in the regime of non-uniform ellipticity. Now, some examples of uniformly elliptic equations. Well, we have the queen of the equations, which is the Poisson equation. If we want to go to the nonlinear setting, well, the Laplacian equation. Or more generally, we can consider nonlinear tensors minus divergence of A of du, where A verifies classical assumptions introduced by Ladygensky and Duraltseva, okay, which essentially says that the Z of A precisely behaves as one would expect from the Laplacian. Okay, so we are considering nonlinear tensors that have the very same ellipticity behavior of the Laplacian. In all these three cases, we see that the ellipticity ratio is uniformly bounded. Okay. Now, one could think that uniform ellipticity is strictly related to a power type growth. Okay, I consider the same power from above and below, and this should more or less determine uniform ellipticity. Okay, this is absolutely false because we can consider more general structures, okay, which, I mean, not necessarily homogeneous structure. For instance, you could think about sum of powers, okay, or logarithmic perturbations of powers. What is crucial is that this relation, okay, in prescribing a sort of proportionality between a twiddle and its first derivative, modulus t, holds. This in particular implies that the ellipticity ratio is uniformly bounded. And operators of this kind has been deeply investigated, okay, over the years, I mean, by lots of authors, Baroni, Beccamingione, Bion, Cianchi and Mazziadini, Lieberman, Strufoni. There are lots of people. In particular, the regularity theory for solutions to this kind of uniformly elliptic equations is very well understood, okay? Now, what happens in the non-autonomous case, okay, when we plug in a coefficient that depends on the space variable? Now, in this case, we are again led to consider the highest eigenvalue and the lowest eigenvalue of dz of a of xz for, I mean, the very same reason that I told you about in the autonomous case. But in this case, both the highest eigenvalue and the lowest eigenvalue need to incorporate a dependency on x, which can be more or less crucial, okay, depending on the structure of the equation itself. Moreover, we need to consider two notions of ellipticity ratio. The first is essentially the same one considered in the autonomous case, and I mean, it worked nicely, so why throw it away? And it is the pointwise ellipticity ratio given by the ratio between G2 and G1, okay? And the new ellipticity ratio, the non-local one, that this time takes into account the ratio between the supremum over a certain ball of the highest eigenvalue of dz of a over the infimum over the very same ball of the lowest eigenvalue of dz of a. Now, what is the need of introducing those two quantities? The first one, in some sense, measures the second, the derivatives of dz of a, okay? And measure their proportionality, if they are proportional one to each other or not. While the non-local one takes into account the contribution of the coefficient and measure how far is the coefficient away from having just a perturbative role of a uniformly elliptic operator. This will be clear in the next slide. Of course, by very definition, the pointwise ellipticity ratio is less than or equal than the non-local ellipticity ratio, of course. I mean, it is definition. But let me show you an operator in which the role of the non-local ellipticity ratio proves to be crucial for determining properties of the operator itself. So if we look at this equation, which is nothing but the Euler-Lagrange equation of the double phase functional dw to the p plus a of x dw to the q, okay, which is quite simple, right? It is p Laplacian plus non-negative weight q Laplacian. That's it. P and q, of course, the interesting case is when p is strictly less than q. And what happens here? Now, if we have a look to the pointwise ellipticity ratio, well, it is beautifully uniformly bounded. So according to the pointwise ellipticity ratio, double phase energy is a uniformly elliptic operator because pointwise is the sum of two powers. That's it. However, the ellipticity ratio, the non-local ellipticity ratio tells you to be careful because you see, A here is allowed to vanish. Therefore, is not positive enough to rebalance oscillations in two different points, okay? Therefore, here we see a pathological behavior, and the non-local ellipticity ratio tells you that the double phase energy has some sort of non-uniform ellipticity, which is not that strong, but still it falls outside the realm of uniformly elliptic operators. Okay. Now, let me just have a review of how to recover Schauder estimates in the linear case. Well, we first noticed that the solution of the Poisson equations are smooth. Therefore, if we add coefficient, and since the matrix coefficient and the gradient stick together, what I expect is that solutions to the non-autonomous equations preserve as much regularity as the degree of smoothness of the coefficients allow. Okay, here A is expected to be bounded and elliptic in this sense. Now, what it turns out, and this is, I mean, classical, is that if A is Elder continuous, then the gradient is correspondingly Elder continuous. And these kind of results are, I repeat, classical, were first obtained by Hopf, Cacciopoli, and Schauder in various forms, all of those heavily relying on potential theory. However, what wasn't taken seriously into account is that asking for Elder continuity of the coefficients means that the oscillation of the coefficient itself can be quantified and can be moreover interpreted as some sort of way of measuring distances between the solution of your original equation and its lifting, okay? The solution of the frozen equation on a certain point, okay? Using this oscillation, is it possible to quantify the distance in average between those two functions on a certain fixed ball? And this is at the core of perturbative methods that are essentially the modern way to prove Schauder estimates for this kind of equation. This was provided by Campanato, Trudinger, and Leon-Simon, okay? And the point here is that exploiting this kind of oscillation, it is possible to estimate the distance in average of those two functions. And solutions to the frozen equations have homogeneous reference estimates, okay? Which means good regularity properties, which means that matching reference estimates, homogeneous reference estimates from the frozen equation with homogeneous comparison estimates between those two, it is possible to iterate and then recover the regularity for the gradient of our original solution, okay? Now, the corresponding nonlinear theory is relatively more recent and it starts beginning at the 80s. Indeed, the underlying idea is always the same. We consider, just for simplicity, the P-Laplace equation, and the possibility of recovering, and notice that the possibility of recovering Schauder estimates is related to the fact that the corresponding frozen equation, okay, which is this one, still enjoy good regularity properties, okay, which were provided by the work of Uraltseva and Uhlenbeck, that prove that solutions to the P-Laplacian equation are C1 alpha 0 regular for some alpha 0 depending on the ambient space dimension and on P, okay? And you cannot do better than this in the light of a counterexample due to Uraltseva. In any case, solutions to the frozen equation have gradient that is Elder continuous. Moreover, homogeneous reference estimates are available. Again, using the Elder continuity of the coefficient, it is possible to measure the distance in average between those two functions. Then matching comparison estimates and reference and homogeneous comparison estimates and homogeneous reference estimates, it is possible to iterate and prove again Elder continuity for the gradient. Now, analogous consideration holds for more general equations verifying Ladijevskaya and Uraltseva's assumptions. This is work of Giaquinta and Giusti, Manfredi, Di Benedetto, Lewis, Tossdorf. And it was recently noticed by Cusi and Mingione that the regularity of coefficients is strictly related, of course, to what kind of regularity you expect for the gradient, okay? In the sense that if you want that the gradient is Elder continuous, then you need the Elder continuous coefficient. However, if you are just content with the continuity of the gradient, you can relax the regularity of the coefficient to Dini continuity. This is enough for proving continuity of the gradient. There are, moreover, several important results also due to Mazia and McCowan, and this is a very interesting recent paper. Now, let me summarize what we got so far. First of all, if you want to prove Schauder estimates in the uniformly elliptic setting, you have to rely essentially on two ingredients: homogeneous comparison estimates, okay? You quantify the distance between your original solution and solution of corresponding frozen problem. Frozen problem has homogeneous reference estimates. You match those two informations, you iterate, you get Elder continuity for the gradient. That's it. And this perfectly works in the uniformly elliptic setting, but fails in the non-uniformly elliptic one. Indeed, proving Schauder estimates for non-uniformly elliptic problems was, huge, let's say a substantial open problem. Okay, now what if I want to bring Schauder estimates into the realm of variational problems? Okay, for minimizers of certain functionals. Now, for simplicity, let me consider just this model example, but of course, what I'm saying holds in a more general setting. Here, assume that f either satisfies Ladijanska and Durazevas assumption, so just take it as the P Laplacian. Now, a functional of this type admits Euler-Lagrange equations, right? Yes, it is this one. Therefore, this verifies this is an equation. Therefore, taking into account that minimizer of these variational integrals are solutions to this equation, we can just recover the whole machinery developed for solutions to equations, to uniformly elliptic equation, and then applying it to the Euler-Lagrange equation of this functional. That's it. So we see that in the variational setting, the crucial tool is the possibility of exploiting the Euler-Lagrange equation. So let's see what happens if the Euler-Lagrange equation is no longer available. We consider this variational integral, okay, where f either satisfies Ladijanska and Durazevas assumptions, or it is again the P Laplacian. Here h is a lower order term that is measurable in x, okay, and then the continuous in w. What does it mean? Euler-Lagrange equation simply doesn't exist. However, it is still possible to exploit perturbative arguments in this framework, okay? And this is work by Frese, Giaquinta Giusti, Evert, and Manfredi. And the perturbation techniques employed here strongly rely on minimality, okay? Another functional on which it is not possible to directly apply the whole machinery exploited for equation is this one, which is in some sense the black beast of variational integrals. Indeed, in this case, we have a term depending on the w variable that is no longer a lower order term, but it multiplies the highest order term. And of course, this immediately falls outside the realm of traditional Schauder estimates. However, when f satisfies Ladijanska and Durazevas assumptions, or just, I repeat, let f just be the P Laplacian for simplicity, we can apply standard de Giorgi theory, okay, to prove that minimizer of this variational integral are Elder continuous, okay, and this comes just from this group, and this is the Giorgi's theory, okay. Here, of course, we are assuming that C is Elder with respect to the x variable and with respect to the w variable. Therefore, as soon as we know that any minimizer of this variational integral is Elder continuous, we see that the composition C of x, U of x is Elder continuous for the good reason that it is the composition of two Elder maps. Therefore, perturbation methods can be carried out again in this framework, and everything goes on smoothly, and provided the gradient of minima of this variational integral is Elder continuous. Now, concerning non-uniform ellipticity, well, there are a series of important works, yet before the 70s, with the work of Ladijanska and Durazeva, Gilbert, Stampacchia, Hartmann and Stampacchia, Ivoshkina and Oskolkov, Serrin, Ivanov, Trudinger, Leon Simon. Lots of brilliant mathematicians that worked on these issues. And also after the 80s, we remember the contribution of Trödinger, Uraltseva, Durdaletova, Lieberman, Ivanov, Marcellini, and Zhikov. What is in particular worth mentioning after the 80s are the contribution of Paolo Marcellini and of Vladimir Zhikov. Indeed, Marcellini introduced a very strong way of approaching this kind of problems by means of introducing the so-called PQ non-uniform ellipticity, which is particularly helpful when dealing with this kind of problems, while Zhikov introduced a series of model variational integrals that are not so non-uniformly, in the sense that models like the PX Laplacian or the double phase, which have this kind of softer non-uniform ellipticity, okay, but they are very instructive for dealing with the more general case, okay. Now some classics, the book by Ivanov, the paper of Ladijinskaya and Uraltseva, the work of Trödinger. This is just a gallery of classics, works of Leon Simon. Okay, let me see what happens in the variational setting when we want to describe what is uniform ellipticity or non-uniform ellipticity. Well, if I have a variational integral of this type, whose Euler-Lagrange equation reads, of course, this way, I can define non-uniform ellipticity by considering what? In the case of equation, I wanted the derivative in the gradient variable of the nonlinear tensor A of Z. In this case, the nonlinear tensor is dz of f. Therefore, the derivative of dz of f in the gradient variable means that I need to consider the ratio between the highest eigenvalue of the second derivative of f over the lowest eigenvalue of the second derivative of f. Okay? And of course, I am in the non-uniform ellipticity regime when this quantity blows up. Okay, now what happens in the case of polynomial non-uniform ellipticity, which means that the ellipticity ratio behaves as a power. Here we can introduce the terminology of Marcellini and consider integrants with ellipticity described by means of two different powers, P and Q. Okay, in such a way that the only bound that we can provide on the ellipticity ratio is modulus of Z to the Q minus P, which blows up when in the interesting case for us, which is the one when Q is larger than P. Now, one could think that the blow up of the ellipticity ratio is strongly related to the regularity of solutions. And just theoretically, one could think that if we want to hope for regularity, we need to somehow slow down the blow up of the ellipticity ratio. This is exactly the case. Indeed, already in this case, in the case of PQ growth condition, already in the autonomous case, for having hopes of regularity for minimizers of this kind of variational integrals, we need to assume that Q and P, okay, are not too far apart from each other. And in particular, their ratio is bounded by 1 plus something, okay, that goes to zeros and goes to plus infinity. And this is a sufficient and necessary condition for regularity, okay? Now, let me recap a little bit what I told you so far. I presented essentially two classical facts. The first one is that solutions to this kind of uniformly elliptic equations admit the following implication. If the coefficient is elder, then the gradient is correspondingly elder, okay? Moreover, second classical fact, when dealing with non-differentiable functionals of this type, then we have that if coefficients are elder continuous, then the gradient is elder continuous, okay? Well, those two classical facts gives rise in the non-uniformly elliptic setting. Okay, the previous two classical facts are, of course, true in the uniformly elliptic setting, but in the non-uniformly elliptic one, they give rise to two quite long-standing open problems. First one is providing Schauder estimates for solutions to non-uniformly elliptic equation where the nonlinear tensor A satisfies PQ non-uniform ellipticity conditions. Okay, is it true that if C is elder, then the gradient is elder? Second open problem, same thing in the case of non-differentiable functionals. Is it true that if H is measurable in X and elder in W, then the gradient of minimizers to these variational integrals with F verifying PQ non-uniform ellipticity is elder continuous? Well, on those problems, there is a huge literature. For instance, here we can see a comment due to Lieberman of a paper of Giaquinte Giusti, which says that yes, your approach is very nice and perfectly works in the uniform elliptic setting, but fails in the non-uniform elliptic one. As in the non-uniform elliptic setting, we need to assume stronger assumptions on the nonlinear tensor, okay, which immediately rule out classical Schauder estimates. Indeed, this is the case. Let's have a look to this theorem by Ladygensky and Duraltseva. It is required that the nonlinear tensor is differentiable with respect to all its entries. Moreover, severe barrier conditions are required in order to provide Schauder estimates. Okay, as Ivanov points out in his book, the crucial point for getting Schauder estimates in the non-uniform elliptic setting is to construct a family of uniformly elliptic problems that approximate our original problem, okay? And there is a sequence of solutions to those approximating uniformly elliptic problems, okay? With uniformly bounded L-infinity norm of the gradient, uniformly with respect to the parameter of approximation that converge to our original solution. So the crucial point here, in order to getting Schauder estimates, is first getting L-infinity estimates for the gradient, okay? And this is also confirmed by Giaquinte and Giusti themselves. Okay, now this talk is to propose a solution to this problem. We can catch both the cases of non-differentiable functionals and equations with elder continuous coefficients that are non-uniformly elliptic. Our technique goes beyond the one of freezing and comparing. It's slightly more indirect, but still we can confirm that Ivanov was right, and the crucial point is getting Lipschitz bounds for solutions or minimizers via approximation by more regular problems. Okay, now let me have a look to this very privileged model, which is the double phase one. Okay, we already seen that for having hopes of regularity already in the autonomous case, P and Q cannot be too far apart from each other. Moreover, as it is, as I told you before, the problem with the double phase is the non-local ellipticity ratio, okay, while the pointwise one perfectly behaves. So keeping in mind this, one could think that since the pathological behavior comes from the coefficient, then for getting Schauder estimates in this case, okay, we not only need to take P and Q quite close, but this closeness needs to be quantified by the elder coefficient of the elder exponent of the coefficient. Okay, so we can also say another thing. It is not only necessary that A is elder for getting Schauder estimates, but this elder continuity must be quantified and needs to interact with the exponents. This is indeed confirmed by counterexamples. Indeed, when dealing with double phase functionals, if we violate a certain constraint that I'm going to show you in the next slide, we can find minimizers whose gradients do not belong to L cube, for instance. So it won't belong to L infinity. And moreover, you can do something even more subtle. You can construct, you can again violate this constraint and construct minimizers of double phase functional, okay, whose set of non-Lebesgue points has almost maximal Hausdorff dimension, and moreover, it is a fractal of Cantor type, okay? And this doesn't make these minimizers any better of any of their competitors, okay? It is, I mean, they are simply as awful as any W1P map, because it is possible to prove that this Hausdorff dimension is strictly larger than n minus p minus epsilon. So it is essentially maximal, taking into account that these minimizers belong to W1P. However, there is regularity, of course, if this constraint is satisfied. Notice this quantity, alpha over n, because it will turn back, okay? And it is significant because since with the double phase, we saw that the problem was in the non-local ellipticity ratio. Therefore, in the idea of freezing and comparing, no, which are the two most important moments when dealing with Schauder estimates in the linear and in the non-linear setting, okay, the problematic behavior of the double phase can be seen at the level of comparing, okay, and this in some sense shows this delicate interaction between the growth exponents P and Q and the elder exponents of A, which in some sense is telling you that the blow up of the non-local ellipticity ratio is slowing down, okay? And this will give you regularity, optimal regularity, actually. And I'm sorry, I should have mentioned that this bound is sharp in the light of the counter examples that I showed you before. Okay, now the double phase functional is pointwise uniformly elliptic, but has a pathological behavior in the non-local ellipticity ratio. Okay, this can be generalized to more general structures, which, I mean, attracted lots of attention recently. Prominent examples, I repeat, double phase P of X and any kind of combinations of this kind of energy. And the crucial point here, and I mean, all these models were recently generalized in a paper by Asto and Dock, but the crucial point is always that all those structures are pointwise uniformly elliptic. Whenever you freeze them, you obtain something which perfectly behaves. So you essentially, under, again, the point of view of freezing and comparing, you have no problems at the level of freezing. The only slightly pathological behavior that you may see is at the level of comparison, okay? So you just need to take care of this comparison issue, which is in general solved by means of getting some higher integrability, okay? For instance, of Gehring type. This is enough for solving this kind of non-homogeneity at the level of comparison. Already, if we are in the framework of PQ non-uniform ellipticity, already in this very simplified model, we see that pointwise uniform ellipticity simply fails. Indeed, whenever we freeze, we get an ellipticity ratio that blows up as modulus of Z to Q minus P. So there are no hopes to treating this kind of problems as the double phase, for instance. Okay, but what I can say is that we have Schauder estimates for the case of PQ non-uniform ellipticity, and I'm showing just for the sake of simplicity, I'm showing this for a simplified model, but we can do for more. We can obtain Schauder estimates for way more general models than just this. Okay, I assume that F satisfies PQ non-uniform ellipticity. C is Elder continuous. Then, as I already told you by the work of Marcellini and Giaquinta and all the counter examples in the double phase case, I need to assume a certain constraint on the exponents to guarantee that the gradient is locally Elder continuous. Now notice this quantity, alpha over n. This is the very same quantity that appears in the double phase case. and accounts for the interaction between the coefficient, in some sense, accounts of, how can I say, it accounts for the contribution of the coefficient, okay, to this problematic situation. And this squared here is due to the fact that the coefficient is multiplying the highest order term, okay? Again, in this setting, I can prove that the gradient is locally at the continuous. Analogous result holds for solutions to non-uniform elliptic equations that satisfy PQ non-uniform ellipticity, okay? And now let's see what happens for non-differentiable variational integrals. I have that F is again PQ non-uniform elliptic, H is measurable in X and Elder in V. We need to impose again as a constraint on the exponents, and now notice that this constraint in some sense reflects the various ingredients considered in this problem. We have alpha over n, this one left 1, I mean with the power 1, because this is not multiplying the highest order term. And in any case, takes into account of this kind of growth. And again, also this component of the bound accounts for the presence of H. And also in this case, the gradient is locally at their continuous under these conditions. More difficult, we include another lower order term that this time depends on the gradient. Here we are assuming that G is convex in the gradient variable, that the second derivatives verify this kind of growth. The oscillation with respect to X and V is Elder and can be quantified also via power of the gradient variable. We will need to assume that alpha plus gamma is strictly less than P and impose again a constraint that accounts for the presence of all these lower order terms. In particular, you see this orange one has the same character G, and therefore we can prove that the gradient is locally at the continuous, okay? Finally, the black list. Also, we can prove Schauder estimates also for this variational integral. We have that second derivatives of f are elliptic in this sense, so PQ ellipticity is satisfied again. C is Elder with respect to both the entries. We need to assume P larger than N, and again, another constraint that accounts for the presence of the coefficient squared as C is multiplying the highest order term. Here we account also for the fact that P is larger than N, which comes from the fact that here we have a dependence on W. And in this framework, we can prove the continuity for the gradient. Now, let me comment a little bit about the assumption P larger than N. It seems to be quite technical, but it is actually natural, because when dealing with this variational integral, okay, with f of the P Laplacian type, okay, we have by the George's theory that minimizers are already Elder continuous, and therefore we are essentially treating a coefficient C of x, U of x, which is Elder continuous. Of course, the George's theory fails in the non-uniform elliptic setting. It is no longer available. Therefore, the assumption P larger than N in some sense rebalance the lack of the George theory, and I suspect that it can be optimal. Okay. Now, I want to conclude my seminar by listing some borderline regularity results and some short borderline regularity results. And for doing this, let me recall this classical theorem due to Stein, which says that if a function has its gradient in Ln1, then it is continuous. This is a sort of borderline case of Sobolev-Morley embedding theorem. Therefore, if I want to give a PD interpretation of Stein theorem, I can combine it with standard Calderon-Zygmunt theory to deduce that minus Laplacian of u equal to something, with this something in Ln1, implies that the gradient is continuous. And this is optimal in the light of a counterexample due to chunking. Okay. Now, one could think, okay, in the linear case, very nice, but what about the non-linear case? Well, in the non-linear case, we have the very same phenomenon. If you solve this equation, okay, and this is a very nice result due to Gusi and Mingione, with C in continuous and F in Ln1, then the gradient is continuous. Notice that the fact that F belongs to Ln1 means that this optimal, because of Chunky's counterexample, condition for proving continuity or boundedness for the gradient of solutions to this equation do not depend on P. Okay, here, I mean, there is no sign of P in this condition. And so one could conjecture, and this is what Uraltseva did years ago, that the optimal condition on the right-hand side of equations of this type that guarantee boundedness for the gradient of solution do not depend on the structure of the equation itself. This is true, and it is true to a very large extent. And moreover, it is neither related to the fact that here we have an operator in divergence form. Okay, what is indeed, this can be proven also for in the fully nonlinear setting. Okay, for equation of the type f of d2u equal f, which are uniformly elliptic. And what it can be proven also, it can be proven also for systems of differential forms and for the normalized P Laplacian. It is a very general property. And what is crucial is that you have enough ellipticity. That's the real point. Indeed, we can extend this result to the case of PQ non-uniform ellipticity with differentiable coefficients. This is what we did in this paper with Mingione. We can prove that if f is in Ln1, then the gradient is bounded, and standard means you get continuity. There is also a result by Beck and Mingione concerning the autonomous case. So let's see if we can provide a non-differentiable counterpart of this result. Okay, I have F verifying PQ non-uniform ellipticity. And this was the very same result that I presented before, when the oscillation of the lower order term can be measured just by the distance of V1 and V2. Okay, in this case, we already said that the gradient is locally Elder continuous. What happens if in the very same framework, I slightly modify the requirement on this oscillation by asking that it is measured by the distance of V1 to and V2 to some power alpha, multiplied by a function that belongs to a suitable Lorentz space, ln over alpha 1 over 2. Under the very same bound, I can prove that the gradient is locally bounded. So this can be seen as a non-differentiable Stein theorem, okay, in the non-uniform elliptic setting. Now we can also obtain analogous borderline regularity results if we give up on the case of polynomial non-uniform ellipticity. So let's consider these iterated exponential functionals, and I will take just other 2 minutes of your time. I don't know if I'm running out of time. I should be. Which, I mean, received lots of attention by Ducanel, Lieberman, Marcellini, and Evans in the framework of weak KAM theory. Okay. So let's have a look to this kind of monster variational integral, which consists of iterated exponentials with coefficients and right-hand side term. Okay, if the gradient of all these quantities belongs to Ln plus epsilon, whatever epsilon you want, and f is in Ln1, then the gradient of these variational integrals is locally bounded. What I would like to stress here is that the fact that the gradient of coefficients belongs to Ln plus epsilon means that coefficients are Elder continuous. But in sharp contrast with what happens in the case of functions with PQ growth, or just think to the double phase for simplicity, here any rate of Elder continuity suffices. This is because the ellipticity ratio is no longer, in the case of functionals with PQ growth, the ellipticity ratio is a power. Therefore, if you want to compare the energy to the ellipticity ratio, you are comparing a power with a power. In this case, the ellipticity ratio is a logarithm of the energy. Therefore, slowing it down is relatively easier and requires a very small amount of Elder continuity. We can bring this problem, this kind of functionals also in the realm of obstacle problems. Okay. Indeed, as it was proven by Fuchs and Mingione, it is possible to linearize, after approximating, of course, this problem. This kind of obstacle problem, it is possible to linearize it in such a way that it is possible to prove that a constrained minimizer of this variational integral can be approximated by solutions to this problem, okay, where now the function f depends on the second derivative of the obstacle and the obstacle itself. Therefore, we have these sharp regularity results, sharp with respect to all the ingredients considered, also the obstacle. Indeed, we can prove that solutions to these obstacle problems are locally Lipschitz continuous, provided that, okay, the gradient of the various coefficients involved belong to Ln plus epsilon, and the second derivative of the obstacle is in Ln1. Okay? And this is, I mean, to see that the sharpness of this result, we just need to have a look to quadratic functionals. Okay, after linearization, you get this. And by standard Calderon-Zygmunt theory, we have that if the Laplacian of psi belongs to Ln1, if and only if the second derivative of psi is in Ln1. And this is again sharp in the light of the counterexample due to chunky, because we are, in the end, we are dealing with an equation of the type minus Laplacian of u equal f with f in Ln1. And okay, I finished, and many thanks for your attention, and thanks for the patience that I cannot.
Thank you, Cristiana, for a fascinating talk. So we do have time for a few questions. If anybody would like to ask a question, then I think you can raise your hand, and you can be unmuted and ask the question, or if you prefer, you can put a question in the chat. Either way is fine, or in the Q&A. Okay, so we'll just wait to see if any questions come through. I just want to ask, while we're waiting, how much of this story changes if you look at the parabolic case? So for example, if you look at the gradient flows of the corresponding functionals, can you still prove estimates of this kind?
I believe yes, this is currently under investigation, and I believe that these results can be brought also in the parabolic framework, yes. The technique that we use should be, of course, readjusted to the parabolic framework, but I believe that these results also in the parabolic setting, yes.
Yeah, okay. I mean, I guess there's a complication there that somehow you have to compare the ellipticity constants also to the coefficient in front of the time derivative, perhaps. So maybe things are a little more complicated there.
It is the intrinsic scaling that is somehow, yeah, not very, but yes, it should be
the same technique should help. Yeah. Okay, interesting. Yeah. Okay, I don't see any other questions so far.
I have one question, Ben.
Daniel, yes, go ahead, please.
Yeah, so it's very funny, this 1 on 5 in front of the condition on Q on P. So how does this come, actually?
1/5, yeah.
1 on 5,
okay.
why not 1 on 6, you know? I mean.
Yeah, well, why not 1/10? No, it is just a way. Okay, let's say that this bound was originally, I mean, in the preprint, there is an expression long like this. So let's say that it is an aesthetic choice, because I cannot put you an expression of these dimensions in the slide. Not, I mean, people is strongly complaining about this choice.
So 1/5 is enough, yeah, okay, good. Right. Okay, I'm just checking the people here to see if there are any other questions. So I know the webinar format is not so conducive to asking questions, but for any of you that would like to have a chat more informally with Cristiana, then you can join us in a few minutes at the so-called coffee break. I think you should all have received a separate email with an invitation to that. So we normally start that just a few minutes after the next hour. Do you have that, Cristiana?
Just a second, that I'm scrolling, but
it probably would have arrived during your talk, I think.
no, wait.
Okay, we'll make sure we send you one in a moment.
And I still have another question, actually.
Oh, Daniel, yeah, another question, yeah.
I have a question. So do I understand it right? Sorry. Do I understand it right?
Yeah.
That the result by Cianchi is optimal, is it right? So the condition.
In Cianchi's paper, there is a counterexample, okay, that shows that if you have an equation of the type minus Laplacian of u equal f, the optimal condition for getting continuity is f in ln1, for getting continuity of the gradient.
Okay, but so what?
Can you repeat? I haven't.
Yeah, sorry. 1 second. There is still another thing. So that Cianchi doesn't obtain only continuity. He just obtains boundness of the gradient, basically. But he has then much weaker conditions. I think that's a paper Cianchi-Mazia, actually.
No. It is just Cianchi, and it is on Journal of Geometric Analysis 93.
Okay.
It is just Cianchi.
I have to check then. Okay, thank you.
No, you're welcome. Okay, I got the email.
Very good. Okay, yeah.
Cristiana, I have just sent you again the link to the coffee break, and if there is a problem, just reply to me. I will send it again.
No, she has it now. That's good. Yeah. Thanks, Ben. Okay, so then if there are no other questions, thank you everybody for attending, and please feel free to join us in a few minutes at the coffee break. Then you'll be able to ask any questions that you have. Anyway, so thanks again, Cristiana, for a very interesting talk.
Thank you.
And, talk to you soon.
See you at the coffee break.
Yes. Okay, see you then.
Bye. Okay, stop share. And
thank you, everybody.
thanks again.